Aloha. I am going to be going through some of the control charts, and we have the ones that we cover in the Six Sigma class. And when you build these, I think the most important thing to do is consider what the data in this graph means. There's lots of different ways to build these. If you go to YouTube or you look at other different courses, they'll tell you how to use Minitab or all these other different great programs that you can use. I wanted to do this in Excel because Excel is a tool that most of us will have. And uh, so that seems what makes most sense to me. The first two sets of graphs we'll make are the IMR and the XBAR ones. These use continuous data. The other ones will use attribute data. Pull this over here. We can look at this. The first data set for the IMR graphs has the total pounds of fish harvested with hand tool permits in Alaska from 2000 to 2022. I'll start off by making the eye chart, individual chart, and I'll do that by populating the mean, 1 and 2 sigmas from the mean. We'll just use a basic the mean formula in Excel is average. I'm going to do that, the average column B. 1 sigma below the mean, I'll do equals the mean minus standard deviation from column B. And then I can take this formula that I have, and I can actually just paste it into here, and I'll modify it because here we're looking at 2 times 1 minus 2 times the standard deviation. This is the minus. We want to do plus also. That will give us our plus specification levels up and below and above. Copy this, and I'll put that in here. Now what I can do is I'm just going to copy this formula all the way down. Okay, so now that we have the total pounds, I'm going to make this into a graph, and I'll call it my eye chart. Yeah, sure. Now that I have, oh, I need to add the year as well. And so I click on this, and if I go up the formula bar, after the first comma, before the second comma, I'm going to add in the X variable. Now we've got all the years in there. I suppose I can adjust this. Man, let's see. The last one is 2022. We really, though, if I was doing a presentation, I might do a lot more formatting than this. I'll just do some basic formatting. Now that I have the number of fish harvested, the total pounds, I'm going to add all of these other things in here that will tell me. I mean, I can sort of see, if I eyeball it, I can sort of guess where the average is, where 1 or 2 standard deviations will be. But once we throw it in here, it becomes really apparent about where we are, if we're in process or not, process control. If we're using 2 sigma, I mean, it looks like whatever type of variability, it might just be common cause variability. There's not a huge lot of change, although, I mean, you can sort of tell, it looks like from about 2013 on down, there might be some sort of a change, a drop in the amount of fish harvested. This is the basic eye chart. Let's look at the MR portion of the chart. The moving range, this is where the values come from. To do that, I'm going to put in a few formulas over here. But before I do that, let me just say there's a couple ways to get the range. One is you could do max of these two minus min of those two, and that will give you the range. The range is the difference between the largest and the smallest values. Another way you can do it, that's an easy way to do it. Another way you can do it is to do equals absolute value of that minus that. That way, if you're going up or down or up, no matter what, you'll have a positive value. You only capture the difference between the two. There's a range. MR is the average of the range. The average range. And to do our upper control limit and our lower control limit, there's a more complicated formula. Oh, I think we can see it. Let's see. It depends on how many things you have How many observations? We only have one, so we'll go with the closest one. We have 3.267. Okay, so we'll do upper control limit equals 3.267 times that. And this one, we put 0 for lower control limit. So now if I want to graph this, we do the same thing for the MR chart that shows the range that we have. Want to have the years to it. Now that the years are on there, I can add these things as well. And so we're looking at the range. Everything above the red bar shows when the change is greater than average. Everything below the red bar shows when the change is below average. There's 1 year. Well, that was there's a big huge spike for this year. It was 2013. Looked like a banner year. You can see that with the amount of harvests that we have. But also that's where the biggest change is from any year. If I'm just here, what happens if we start putting values? So if there was no change at all, I'm just making up some data points. Oops. If I start adding these, if there was no change, you would see where the MR chart goes down to 0. There's the MR chart. And with the MR chart, otherwise known as individual and moving range charts, both of these are control charts that you want to use to examine continuous data. Together, they can give you the complete information on process behaviors. If you need to measure and examine, measure data for individuals rather than entire subgroups, and then this would be your ideal option that you want to use. What happens if you have subgroups, if you have higher volume? Let's go to the X bar in our charts. Here we have some process where we made something with the X bar in our chart. We were a subgroup of more than one. The R chart shows the sample range, which represents the difference between the highest and lowest value in each example. We'll see that in just a second. We're going to start off by populating this table. And to do that, we want the average. We took 4 different measured values. So I'm going to take the average of what we measured, and I will populate those here. And as long as you have consistent number of 4 samples with each of these, you can do, if you did average this, you'll notice, what is that, 38.48 or 38.5. That's really the same thing as averaging all of this. And then when we take the standard deviation on here, we are going to equals standard deviation this. I'm going to populate this with the standard to SDEV B3 to E3, and I'll copy this all the way down here. If I sum this, I'm going to do the same thing where I sum this, and this will give me, I want the average of the standard deviations. Using these to help build our graph, and I'm going to, for here, X bar, I'm just going to say equals F6. That's your X bar value. And our S bar is going to be the value that we calculated right here. We're going to, for our upper control and lower control X bar, and the S chart as well, we're going to use these formulas down here. X bar plus A3 times S bar. So that means it equals X bar times, and then I come over to this table to the right, A3. And 1, 2, we've got 4 samples. So that's going to be this thing right here, corresponds to N of 4. So that's 1.628. Take that and times S bar. S bar is this value right here. And actually for this one, I'm just going to anchor this one. I'm going to copy and paste the formula. So that is, oh, I need a plus sign in here, not multiplication. So that gives me the upper control, upper specification level. That's a plus. This one's a minus. So I'm going to put a minus sign right here. This next one, B4. If I come over here to where B4 is, go down to 1, 2, 3, 4. That is that value. I'm going to anchor times, what do we want? S bar, this value right here. B3, which is B3 is 0. Okay, we're only going to be looking for samples each time. And so we're going to put 0. I could do equals 0 times S bar to make it more technically correct, I guess. Okay, and then I'll just populate this graph up here. Use upper control limit X bar, that is this thing right here. Lower control limit X bar, that's this value F20. Upper control limit S chart, that is this value right here. Lower control limit S chart equals, that's going to be 0. Then with each of these, it's just going to be the one right above it. So I'll copy that formula equals, we want the same value. These just give us the conclusion. These just tell us where we are, if we're in limits or not. And these ones I'm using, okay. So now if I want to graph this out, I'll make the X bar chart. I'm going to actually go insert. And I'll label this X bar. To take these out. They distract me a little bit. If you like them, keep them, great. And then I'll add these things here. Actually, X bar. So yeah, here I can see that the samples, at least initially, were above average. There was a period when they were below, then they're above again. It looks like I've got a few points. You know, I'm going to, just to make this easier for me to be able to interpret, I'm going to add markers to this one. Let's see, add automatic. There, that's something. And so I've got that one, which is right on, oh, that's right there. I guess that's marginally okay. But like that one's not very good. That one's, well, these are averages. That's outside of our specification limit. So is that one. This one right here, right there. And so I mean, there's a little bit of variation. We have some points that are outside of where we want. Let's look at the S chart so we can get a better idea of this variation. I'm going to grab this, insert. And then we can grab all the same information from over here. And then you can see that the variation is higher among a couple of points above average and where it's below average. And you have some points that are way out there. We call this the S chart. Standard deviation. So we have some process that's going on. We mapped it out with these graphs. We have what happens. We can look at the sample range, look at the difference between highest and lowest value of each sample. What happens if you implement some sort of a training process? I'm going to, because of how I set up the formulas, I'm just actually going to take all these values right here, copy them, and paste them right here. This will update with the new measured sample. So after we implemented some training or some sort of process improvement, let's look to see if we are in better control of what's going on. I copied the graphs as well. And I'm going to go through each of these. These were the data that we have from here is from row 3 to 14. I can come over here to, and I want between 27 and 38. So I'll make these 27 and 38. Although specification levels are a lot more narrow, but I think we'll see some other changes here as well. 7. Okay, look at that. We go the range on here. What is that about 30, 32 and 3/4 or 30, something like that. Oh, 30. Oh, I've got the data right here. 32.8 and 36.7. That's much more narrow. So you have a much more consistent process going on here. Let me put the 27 and 38. We do the same thing with this one. Might as well. Even though those are all values of 0, I should be consistent. 27. And so if we're looking at the standard deviation of the samples here, there's a huge range right here, the very small range. All of these are within control. And so whatever process improvement we put into place, we definitely have some strong evidence that we're a lot better off. Great. That is our chart. Let's take a look at the C chart. Let me come over here. The C chart used to monitor the number of defects where each item can have multiple defects. You should use a C chart only when your subgroups are the same size. And you use the control chart to monitor process stability over time. You can identify where you have and help you correct some instabilities in some sort of a process. Or maybe you can at least do a fairly quick and dirty analysis to see if maybe something you're doing has changed or something might be falling out of order. And this is a fairly easy graph to make. Number of defects. We take the average, we pull some samples, we counted the defects of here. So I'm going to average, let's see, I'll average these. This is the average of everything. So because we can do either the average of all of this or the average of column I, it'll come to the same once we have everything in there. And this one, let's do 2 standard deviations from the mean. That way we're looking at a 95%. So equals J2 plus 2 times standard deviation from all of these. And I will minus. I'll just copy this all the way down. If I'm looking at the number of defects, I can do insert. There's some defects that we have. Yeah. And if I want to have a little bit more attention to the rate of change, I might adjust some of these. Let's see where I want to go. Maybe I'll change the axis options on here. Minimum, I guess I can go 33. Maximum, 54. And it looks like the process here is fairly stable through time. There are some points where it goes up and down. You know, if we look at the rules where you have things go up and down, that might give us some attention where we want to look at why things are changing. but they don't seem to be very far within 2 standard deviations of the mean. Oh, I guess I should label this one too. Add chart elements, chart title. This is our U chart. Great. Now let's look at our U chart. That's the next one that we have. The example I have on here, actually, the U chart is used when you have a number of units so we sampled at some time point, and a per unit average number of nonconformities will be obtained. So we have things like infection, and when we do something a little bit, I guess, when you look at infections, usually the numbers of infections that occur is usually really small. And so you might do something like per unit infections per 1,000. That way, you're not looking at 0.002 or some really small number. You're looking at numbers that more closely approximate integers. So that's a little bit easier to understand. So I'm going to put a couple things in here. We're going to sum everything up here with these totals. And I'm going to, for this one, I'm going to take this number, device days, divide it by 1,000. That way we can look at, because of that, remember, we're looking at units per 1,000. Nonconformities, that's going to be the number of infections divided by the subgroup. And because we made it per 1,000, we're looking at a value of 2. I mean, if instead of that we did number, for everything, we're looking at some really, really small number, which makes it harder to have that number. It's not quite as clear, which is why we did that per 1,000. Let's see that. We're looking at two per infection per 1,000, and then actually you can copy this all the way down here. And so really what this tells us is we have 1.4 infections per 1,000 that occurs. Well, I guess you want to sound more official, 1.38. So we'll do the same thing. We'll look at the process mean that we have here is we calculate it right there. The upper control limit is we're going to look at so the mean plus, this time we're going to do 3 times the square root, and then we're going to look at the mean divided by the number of, let's see, the value, the per 1,000 number we're looking at from column D. That will give us, depending on your industry standard, you might use 2 or 3. The difference between 2 or 3 standard deviations, if you're looking at 2 standard deviations, then you want your upper and lower control limits to be at least 95% in there. If you're looking at 3 standard deviations, that broadens up. Then you care about 99.7. I'm gonna put a minus in here instead of a plus. And really, these numbers are going to be all exactly the same with the one above it. So I'll put in that formula. And now we can graph these. And I'm going to put this to insert. There's our nonconformity per inspection unit. And then I'll throw these in here as well. And I just noticed some. Oh, actually, there's a couple of things I want to do differently. Hold on a second. I'm going to add the month when that occurred. But I think I also want to add one more formula. I'm just going to throw this in here first. It doesn't make sense to have negative infections. And so to add to this, I'll write max of 0 or the formula. That way, there we go. It throws it down. It gives puts a floor of 0. And so really, if we're using 3 standard deviations. It doesn't look like we're out of specification for any of these months. There are some periods when it's higher than others. Oh, you know what? I didn't. And somewhere it's lower. Well, I wonder why the month didn't happen. Month is supposed to be populated here. I probably just grabbed the wrong graph. Change chart type. No, I don't want to scatter out. Maybe I want to combine. Is that what it is? No, nice. Let's see. There we go. Or not necessarily smooth. I don't want stacked. Okay, let me just, sorry about this. Line, need some line. Oh, you know what? And I realized something. And so I do want to have these will change, and that will change too. So if I'm doing it within 2 or within 3 standard deviations, the industry standard actually has 2. I guess I can change that. So depending on whatever it is you're using, make sure you're consistent. But another thing that you'll notice about these, so we have our process mean is straight. We have what happens, some of these are higher or lower, but you'll notice that one thing that's different about the U chart from all the other charts, U chart. The one thing that's different about this chart compared to all the other charts is that your upper and lower specification levels are not exactly, they can fluctuate. They're not constant like you see with the other charts. That brings us to the NP chart. The NP, these next 2 charts they're a little bit different. These ones, so like with the U chart and the C chart, they follow a Poisson distribution. The NP and the P charts, they both of these follow a binomial distribution. And you might measure, this one you can use to measure the number of defective units within a constant subgroup type. And you want to help us determine if the process is stable, predictable. You'll be able to monitor effects of the process improvements over time. The formulas that we'll use for here, some of these are pretty simple. Like what you might, let's see, we'll have the P bar equals average. Like with this example, I think I found online, if you're pulling a bunch of, well, it's modified from something else. But if you have 50 beats and you pull out with our blue and green beads, what's the likelihood that you pull out of a set of beads that you pull out all the green beads? And it looks like, these people pulled these samples out, and see Tom pulled an average of 31.5 green beads. And LA pulled 31, and the numbers vary depending on what they're doing. The grand P bar was average F. So we have the averages for each of the individuals, and then we also have the average for everything. The upper and lower control limits, these formulas, this one's a little bit more complicated. So we're going to take that average that we have, and then if you're doing 2 or 3, I guess this one I'll put 3 times. And then the way you calculate standard deviation is square root of G2 times 1 minus, and then the average. And then because you're looking at an 50 observations, you divide it by n, or in this case, it's 50. And that gives us the upper control specification level. I'm going to do that for the lower. I'll just put a minus sign. And then I'll just copy that all the way down. If I throw this into a graph, insert. Okay, that's a scattered. Let's see, where do I want? There we go. It's a line for sure. And I suppose I could put each individual person on here too. And then I can throw all these other things in here. with my specification levels. And so now I'm looking at this. It looks like Kinesi has, oh no, that's Arihi has a value that's, they pull far fewer green beans. So, so Arihi gets a lot of blue beans compared to other people on average. And you can tell who's above an average for the green beans. So they might have some process where that could be important to be able to monitor what those are. And there is the NP chart. I'm going to add the title on here. And this one is similar. We have, let's look at the P chart. The P chart is used to monitor proportions of defective items. But rather than just counts, we're looking at proportions. And this is where items can be classified into one of two categories, such as pass or fail. And that's why we also use the binomial distribution. And you want to use this control chart to monitor process stability over time or help identify and correct instabilities when they're in the process. And we'll make a graph and we'll see what kind of stabilities or instabilities we might be able to identify with this. And so with this one, let's see, number of defective units. So see the proportion of defective units is going to be 2% for that one. Let's copy it all the way down. We've got a whole bunch on here, which is fine. And so let's look at the average. So I'm going to sum of C divided by the sum of B, that gives us an average value. Then I'll just copy that all the way down. I guess I could copy that. Well, either way. And then when I calculate the upper control limit, I'm going to do P bar plus 3 times the square root of this value times 1 minus E2 and then divided by N. And this one we're looking at the number of invoices and we're trying to see if we can the proportion of there. So I'm going to hit. Okay, and then I'll take this, that's a plus. And then I'll put minus. And oh, you know, we have negative. Negative doesn't make a lot of sense, so I'm just going to put max 0 or the formula. Okay, we'll give this an upper and lower control limit. We can graph these out. Insert. Fraction defective. And then I'm going to add a balance we can figure out. Okay, so if we're using 3 standard deviations, we can see that there's a lot, it goes up and down. So they have really good days and really bad days. But there is something, I mean, we're looking at the number of defective units in the first half until we get to about 0.51, which is about half. We can see that if we were to add an average for the first half and then an average for the second half, you know, you'd see a much higher average for that first period compared to the second period. So something happened, either employees, well, there's a whole structural change. You don't have to, I mean, you don't have to use a bunch of fancy statistics to see that. Where there's some structural change about halfway through, where the number of defects went down a lot. And you're going probably an average about 6% earlier on and down to about 3%. And so this is where this type of a chart would really shine. So you can identify if you have some sort of process that's either improving or maybe you need to take a look at something else. Anyways, I hope this was useful in going through each of these. Please let me know if you have any questions.